Now we are going to study the basic range. So what is range? Range is equals to C delta T by 2. Now what is delta T? First of all, what is range? This is my antenna which is going to transmit the signal to the target to determine the range and the location of my target. Okay, so this antenna will going to transmit the signal. It can be in the form of pulse or continuous wave. Okay, so transmitted signal from the earth station to the target is having a specific time, okay, and specific frequency. So the signal is going to be transmitted from the earth station, or we can say the radar antenna, to the target, and the signal is going to be reflected back to the radar antenna. It is going to be received by this antenna. So this reflected signal is known as the echo signal. Alright. We are going to calculate the time delay between the transmitted signal and the echo signal. Right. So that total time is called the delta T. Alright. C is the speed of light. So we are able to calculate what is the range of my target or range of my radar. How far my radar is located or placed in the atmosphere. Okay. So this is the basic radar range. Now let us calculate one example based on this basic radar range equation. The question is, how far away is a contact if it takes a 33 microsecond for the pulse to detect? So we can say that delta T is given 33 microsecond. Alright. The value of C that we know that 3 cross 10 raised to 8 meter per second. R is equals to C delta T. That is delta T stands for total time. It is already given. 33 microsecond is required if it contacts the target. Okay. Delta T is total time divided by 2. So I can say that total range is 4.95 km by solving this equation. So what is the use of it? We can say that my range of my target is up to 4.95 km. That means after 4.95 km, my radar is not able to detect any object or any target. It will detect up to the 4.95 km. Alright, so this is called the radar range. So there are total 3 types of radar range. One can be minimum range, unambiguous range, and the range resolution. There are 3 terms. First, the shortest range at which a radar can first detect a target, that is called the minimum range. You can identify by C by 2 into pulse width. That means what is the width of my pulse. Second, unambiguous range. So it is the range beyond which my target appears a second time around. What does it mean? That means if I am going to transmit the signal from the earth station to the target, that is my transmitted signal. But by the time, if I am not going to receive the echo signal of this first pulse, after some time, my target will not send echo signal to the earth station. So, my radar antenna will transmit a second pulse, and then after my target is able to send an echo pulse of first pulse. So we can say that this target appears to be a second time. So it is the maximum range beyond which the target appears at the second time. Okay. And third, what is the range resolution? So range resolution is the minimum distance between the two targets which are nearly at the same range that generate a two separate results. Alright, so it is C by 2 PW upon PCR. Now we are going to derive the equation for the radar range. Before that, we must know what is my output power. So we are able to assume that the pulse radiates a power uniformly out from the antenna in all directions. So which antenna is going to be used? Omnidirectional antenna we are going to use. So the power density at a given point is P is equals to P peak upon 4 pi r square. What is R? R is the range, and P peak, that means my peak power. Okay, so peak power divided by 4 pi r square, that will give you the output power. Now, effective antenna aperture. What does it mean? And what is the importance of effective antenna aperture? We can say that the effective aperture measures the actual performance of antenna, right? Both transmitter and the receiver antenna. Larger the aperture, better the radar's performance. It can be a physical aperture or the effective aperture, right? If the physical aperture is large of my antenna, that means it can receive the signal. Reception of signal capability will be going to increase. But there is a no antenna which has efficiency of 100%. Right? Always be a less than a 1. Okay. So what is the effective aperture? Effective aperture AE, that is equals to the antenna efficiency multiplied by the antenna physical area. Alright, that is AE. Now what is directional gain? The omnidirectional beam which spreads spherically in the surface area of 4 pi r square. Right? So we can say that the directional beam or the surface area, it can have two angles. One is vertical, that means r phi, another one is r theta, that is a horizontal angle. So directional gain is the maximum radiation intensity divided by the average radiation intensity. If we can say with respect to power, so it can be a maximum power per steradian divided by a total radiated power by an isotropic antenna. Alright. So based on the dimension and the shape of the antenna, we are able to derive the directional gain. Right? So GB, that is a directional gain, is equals to 4 pi r square upon r square theta phi, theta into phi. Right? So r square is going to be divided, it can be cut. So final directional gain is 4 pi upon theta phi. Alright. Now, what is the importance of power gain? We can also say simply a gain, right? So the power out with respect to the signal losses between the transmitter and the receiver, we can say this is my power gain. Okay. We know that for radar antenna, theta is equals to k lambda upon L. Right? K is the constant, L is the length, and lambda is the wavelength. So which includes the efficiency of radar based on the shape of my antenna. Okay, but we know that for the directional gain, it is 4 pi upon theta phi, but the value of theta is equals to k lambda upon L. Alright, so we are able to derive the equation for the directional gain, that is 4 pi a upon k square lambda square. So we are going to take into account the aperture efficiency AE. By putting the value of AE over there, we are able to calculate the value of the power gain. Alright, so that value is 4 pi AE upon k square lambda square, because we know that what is theta? Theta is equals to k lambda upon length, and phi is equals to k lambda upon width, because theta is the vertical angle and phi is the horizontal angle. So we need to take into account the width when we are going to calculate the phi. Okay? Let us take one example. The question is, what is the gain of a specific radar which is mentioned AN/APS116 S3 radar, which is operating at specific frequency, that is called 9.8 GHz. The antenna is 1.07 meter wide and 0.61 meter height, that means length, with an efficiency estimated at 77%. So, what is the value of gain? We all have the equation that G is equals to 4 pi AE upon lambda square. The equation for effective aperture, we are able to calculate the value of lambda because we know the value of K and value of the frequency. So from value of C and F, we are able to calculate the value of lambda, that is 0.03 meter. And by placing all these values in the equation 4 pi AE upon lambda square, we are able to calculate the value of gain, that is 9061.6. Alright. So over here, from chapter number 1, if you have any question, you can ask me at any time on my below email ID. So in this section, we have covered what is radar, where it is used, what is the full form of radar, then how we are going to transmit the signal from the radar to the target, the basic radar range, the radar range equation, and how to calculate the directional gain and the gain of any radar. Okay? But still, if you are able to find any question, you can ask me at any time on my email. Till then, thank you for your attention.